In this video, I will discuss some aspects related to the application of life cycle assessment, LCA, to assess the environmental impacts of critical raw materials. A dedicated ISO standard defines the standard approach to LCA. The standard phases include the definition of the goal and scope of the study, the collection of the relevant data for unit processes in the inventory analysis phase, the evaluation of impacts in the impact assessment phase, and finally, include the phase of interpretation of results. This standard also applies when using LCA to assess critical raw materials. In the case of critical raw materials, the stages of a life cycle can be distributed across the sectors of the economy and across geographies. Thus, studying the life cycle stages that are relevant for critical raw materials using LCA provides us with a comprehensive understanding of the entire system. Let us consider an illustrative example. Think of the rare earths, a class of critical raw materials that are used in our energy technologies. Rare earths are mined only at specific places across the globe, using heavy machinery and considerable inputs of energy. Natural resources like water are used in the mining process, and toxic chemicals are also released. Furthermore, energy-intensive processes are used to refine the ore minerals and obtain metallic forms of the metals for general use. Subsequent processes of powder metallurgy are then used to transform the materials into subcomponents that are used in final products. All of this would be included in an LCA of a product system containing rare earths. Let's consider the example of neodymium. In this case, the extraction phase will likely take place in China, with local emissions also taking place in China. On the other hand, all processes related to the end of life will take place all across the globe, depending on the end use of neodymium. Typically, these metals end up in magnets, which are used both in cars and wind turbines, for instance. These are truly global products with a variety of end-of-life options. By considering the full life cycle of product systems, LCA allows avoiding the shifting of burdens from one place in the globe to the other, and from one stage of the life cycle to the next. In comparative assessments, alternative design choices can also be compared, and alternative policy scenarios implemented to test their benefits on reducing environmental impacts. Take the example here. Wind turbines do not have emissions during their use phase. They could be considered as a truly green and sustainable technology. However, a system of unit processes and complex interactions is still triggered to put wind turbines in place and to produce electricity from wind power. The production of wind power triggers a variety of impacts across the full life cycle. As mentioned, neodymium magnets are used for many designs of wind turbines to support the functioning of the rotors. All of the inputs, processes, and emissions needed to be considered when assessing wind energy. Therefore, all wind turbines that use neodymium magnets will include environmental impacts related to the extraction of neodymium from the earth crust and the further processing of the minerals into magnets. The possibility to assess such complex systems makes LCA the methods of choice when alternative solutions for sustainable development need to be compared.